Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I think we should get started. What do you think? All right. Gives me great pleasure to introduce Krishna Gumadi. Krishna is a graduate student at the University of Washington, and he's going to be talking today about measurement-driven modeling and design of internet scale systems.
Thanks, Alec. It's great to be here. Thanks for inviting me. And today, I'm going to talk about my work, which is a measurement-driven approach to modeling and designing internet scale systems. Now, I'm going to begin this talk with a very high-level description of the problem that interests me. The internet, as you all know, it's very huge, it's very complex, and it's always rapidly changing. A decade ago, everybody was talking about the World Wide Web, the clients, the servers, the proxy caches, and so on. Today, people talk about peer-to-peer file sharing systems, such as Gnutella, Kazaa, eDonkey, and content delivery networks, such as Akamai. In the future, many expect applications such as voice over IP and massively multiplayer online games to be the next wave of killer applications. Now, to design the internet and the applications of the future, I strongly believe that we need to understand the internet of today. But unfortunately, and perhaps actually ironically, we don't understand how the internet we built actually works. Now, the reason for this is that each one of us owns a separate part of the internet. So while we understand how the portion of the internet that we own or that we built works, what we don't understand is what happens when these various different bits and pieces come together to work as one single entity. Now, the only way to understand a distributed system like the internet is to measure its behavior, model its properties, and experiment with it by deploying new systems. Now, all these three aspects of understanding the internet are very challenging. First, gathering data over the internet is pretty difficult. The internet is simply too huge to be measured. The various different networks and the applications that constitute the internet are all very different. Furthermore, the internet is actually a pretty hostile environment to conduct the measurement studies. Over the past few years, I've lost count of the number of angry emails I received from various different ISP operators for just sending measurement traffic to their networks or their web servers. Now, even if we were to solve the problem of gathering the data, we still have the second problem of analyzing the data. Over the past few years, I gathered over 2 terabytes of data. The problem with having so much data around lies in identifying the few aspects of the data, the few factors that really matter. Now, finding this right insight is almost like searching for a needle in a haystack. And it's probably much worse because when you do these measurement studies, often you do not know ahead of time what factor or what insight you're looking for. Now, finally, experimenting with the internet is pretty difficult too. It's hard to test various different design alternatives by deploying internet scale systems. No one single person owns the internet to give you the permission to deploy these systems. Furthermore, these systems are hard to simulate because the internet is too complex to simulate. So to meet these three challenges, we need three things. First, we need new measurement tools and data that would enable us to discover new properties of the internet and its workload. We need new analysis techniques that would help us explain the fundamental underlying causes of these newly discovered properties. We need new analytical models that would expose the inner workings of these internet scale systems. And finally, we need to leverage the insights from the measurements and the models to design, implement, and test new systems. Now, in the past, my research has focused on all these three aspects of understanding the internet. And today, I'm going to focus or discuss my work on 2 emerging trends. One in internet workloads, and the other in internet routing. Now, both these trends are very popular, but they're very poorly understood. And I'm going to show you how, using a measurement-driven approach, first, we can understand these trends better, and second, how this understanding can help us construct new workload models and design better routing systems. So in the first part of the talk, I'm going to focus on internet workloads. As many of you might already know, recently, peer-to-peer file sharing has exploded both in terms of popularity and in terms of use. And our goal today is to understand how these peer-to-peer workloads differ from the traditional web workloads, why they differ, and what are the implications of these differences on the design of the delivery infrastructure. Later on in the talk, I'm going to focus on internet routing. Our goal here is to understand internet path failures and internet routing in sufficient detail to be able to design simple yet scalable path failure recovery schemes. Okay? So with that, I'm going to dive into the first part of the talk, which is an analysis of a peer-to-peer multimedia file sharing workload. Yes, Chief?
Maybe you'll come to this later in the talk, but about 2 slides back you said that you need new measurement techniques, new modeling techniques,
yes,
without ever saying what was wrong with the ones that people currently use.
So
currently there is a lot of modeling work going on. People have done a lot of modeling work, going all the way from basic queuing theory and whatever, heavy tail distribution, whatever, all the stuff. And then measurement, there is enormous amount of work, right?
Yeah.
And so what is wrong with all that stuff that you need new measurement techniques? Is there like a generic flaw in that?
That's a good question. I don't think there is anything wrong with the measurement techniques. It's just that primarily because of the fact that internet is changing so rapidly and you have these newer systems coming in, you discover the need to measure newer properties or properties on scale that you did not need before. So essentially, the demand as the internet evolves and as new systems come into place, you need to essentially design new techniques, partly to measure new systems, and also to partly to measure the existing systems on a scale that they have not been measured at before. It's more because of the evolution of the internet. I don't think there is anything particularly wrong with the previous techniques. And also, I think in the past, internet measurements have really taken off only in the past 5 to 10 years or something like that. And I still think we're pretty much in the initial phases of understanding the internet. We still don't understand much about it. In fact, I'm going to conclude the talk with a question that actually challenges various different network measurements that we're doing today. Okay? So, let's
quantify that statement that you just made, or is it something that you made because you think that's the case? That is, the current tools cannot really measure and cannot scale up, or the new services that's coming up, you can't really measure them with the current tools.
Yes.
Is that quantified in some sense by you, or?
I can give you examples, specific examples. Like, for example, as part of this research, I designed this tool called King, which enables you to measure latencies between arbitrary pairs of nodes in the internet. Now, previously, people could measure latencies of the internet from points or vantage points that they could control. So essentially, this tool is now being used for essentially evaluating several distributed systems, like the peer-to-peer systems, and whenever people propose locality-aware architectures, to evaluate them, they need this data. Now, both in the past SIGCOMM and in the past NSDI, there have been papers that were published which essentially use this King tool to measure latencies between a much larger number of nodes. That's just one example, but there are many other examples like that. Okay. So let me start with this peer-to-peer multimedia file sharing workload. Now, peer-to-peer file sharing refers to individual users exchanging or swapping music and movie files using their desktop computers. Now, peer-to-peer file sharing is a very recent phenomenon. So before I talk about it, I want to take a step back in time and look at what the internet was like before peer-to-peer file sharing took off in the year 2000. Now, in 2000, the web had already dominated the internet for almost a decade. Tremendous amount of research, both in the industry as well as in the academia, went into designing the infrastructures for delivering the web workloads. Infrastructures such as clients, servers, proxy caches, server clusters, content delivery networks, and so on. Now, most of these infrastructural designs rely on few critical but well-studied and well-understood properties of the web workloads. First, the web workloads comprise of very large number of very small files. Typically, the web objects are 5 to 50 kilobytes in size. That's primarily because they contain text or images. Now, there are few popular objects in the web, and these objects are repeatedly downloaded by many different users over time. And most of the web system designs are, in fact, optimized to exploit this locality or cacheability in the workload requests. In fact, researchers have shown that these request distributions are well modeled by what is known as a Zipf's law. Now, Zipf's law simply states that the number of requests that go to the nth most popular object is inversely proportional to n raised to alpha. where alpha is some constant which is typically close to 1. So in this graph, I show the web request distributions from a trace that we took at the University of Washington border routers. X-axis shows objects ordered by their popularity. So the point 100 refers to the 100th most popular object. Y-axis shows the number of requests that go to this web object. The green curve shows the web requests, and the red straight line through the green curve shows the best fit zip distribution for these requests. Now clearly, the web follows the zip distribution pretty closely. In some sense, zip is kind of an ideal distribution for the web workload. First, it's very simple. Second, it intuitively captures the most essential characteristic of these web workloads, which is that you have a small number of files which are very, very popular and a large number of files that are very unpopular. And finally, researchers have also observed that many of the experimental observations about the workload cacheability can be predicted by this very simple equation. So as a result, this Zipf's law was widely used for designing many of the web system designs that have dominated the internet at the end of the last decade. Now in 2000, peer-to-peer file sharing began to take off with the release of applications like Kazaa and Nutella. Now let's look at what impact this peer-to-peer file sharing had on the internet just within a span of 2 years. Just 2 years later, in the year 2002. Now, this graph shows the bandwidth consumed by the peer-to-peer and the web applications at the University of Washington border routers in May of 2002 over a period of a week. X-axis shows the days of the week, and Y-axis shows the bandwidth in megabits per second. In green, I show the peer-to-peer bandwidth, and in yellow, I show the web bandwidth. Now, this graph shows that peer-to-peer consumes 3 times as much bandwidth as that of the web. Now, when we looked at this graph for the very first time, we simply couldn't believe it, because just within a span of 2 years, peer-to-peer came out of total obscurity to completely dominating the internet. Now, if you think about it, it's in fact much worse, because we just spent a decade designing the infrastructure to deliver tiny web pages, only to find that the internet is being dominated by a completely different workload, one which has very large multimedia files. So this naturally raises several interesting questions. Yes, Victor.
Isn't this a little bit of a very strong statement to make that use that the internet is being dominated by that traffic when you're, from what you just said, you confine your studies to University of Washington rather than, let's say corporate enterprises and just general internet usage?
So,
I mean, students are more apt to use P2P and file sharing. We've known that for a long time. Mm-hmm. But from there, taking the leap to the internet being dominated by that, I'm not sure.
Yes. So that's a very good question. This is about the representativeness of this measurement. Now, we studied the university traffic, but there are other studies done, including one very recently, about 2 months ago, by CADA, looking at the traffic that was going on the backbones of Sprint network, I believe, or Sprint or AT&T, one of those backbones. And they essentially found that peer-to-peer traffic is still dominant traffic in terms of the number of bytes. Now, there are some who question whether this peer-to-peer traffic is something that is going to be sustained in the future, because there are some legal questions about the peer-to-peer file sharing as it exists today. Now, I'm going to argue in a couple of slides later why this is more of a property of multimedia workloads rather than peer-to-peer file sharing. That is, I want to distinguish between the workloads and the infrastructure. Today, these multimedia workloads are being delivered over peer-to-peer file sharing infrastructures. Tomorrow, they might be delivered in a more legal fashion, in a more centralized delivery fashion. And I'm going to argue essentially that it is more of the property of the multimedia workloads rather than the peer-to-peer infrastructures that is making this happen. And hopefully, I'll revisit that question at that point of time if it's still not clear. Yes.
Just have one clarification question. When you say multimedia workloads that these peer-to-peer file systems generate, it's essentially a data transfer workload. It is not multimedia workload in the sense that there is a streaming video or streaming audio going on. Or is that the case you're talking about?
By multimedia workloads, I mean essentially the video downloads. But it's a download. It's not a
download. It is essentially an FTP connection. You can
yes.
think of it like that.
Yes.
Okay.
That's true.
Yeah. Okay.
So when you say multimedia downloads, is that a euphemism for really, really big files? I mean, is there some aspect of the fact that it's a movie that's important, or you just mean it's a really big file?
Yeah. I will actually be talking a lot about that pretty soon when I talk about the multimedia workload characteristics.
Okay.
I think it has got to do something with video. And I'll talk about it when I discuss the model for multimedia workloads.
Okay.
Yes.
Just to
Sure.
just to be sure, we are talking here about large file transfers done over TCP connections, right?
Yes.
Okay.
Yes. So the two questions that are interesting are, how do these multimedia workloads differ from the traditional web workloads? And second, what are the implications of these differences for the design of the infrastructures that we use to deliver these workloads? So to answer these questions, we looked at a popular peer-to-peer file sharing system, which is called Kazaa. Now let me give you a brief overview of Kazaa. In peers, the Kazaa peers are individually owned computers that are mostly connected using modems or broadband. Now there is no centralized infrastructure for Kazaa. However, it does have a two-layered structure. That is, some of the peers, especially the well-connected peers, are classified as supernodes. And these supernodes index the content from all the other peers, and they're useful when you're searching for the content. Now, Kazaa protocol is by and large proprietary, and we had to reverse engineer it to conduct our measurement study. So the data from the study is captured during a 6-month-long trace of Kazaa at the University of Washington border routers. Yes,
with those centralized components, how do you start looking for something? When you're looking for a file, let's say,
yes,
in this system, how do you start?
You mean how does a node bootstrap itself into the system?
Yeah.
So typically what happens is you keep a cache of the hosts that you have connected the last time you logged onto the network.
Let's say this is the first time.
Okay, if you're a very first time user, then essentially you get them from the Kazaa Central website. But that happens at the time when you are essentially joining the system for the very first time. But once you get your software, then from that point on, the system maintains by itself.
You never go back to the central server? So what if I was inactive for a very long time and essentially my cache list is completely stale?
Yes, in that case you might have to go to. But most of the activity happens in a decentralized fashion. I mean, most of it. That's what I meant by decentralized. So we looked at, to capture this trace, we looked at all the traffic that was coming into the University of Washington. We looked at all the bytes. And we identified the Kazaa bytes based on port numbers and HTTP headers. So here are some very high-level characteristics. We saw over 600,000 unique objects and over 1.6 million requests for these objects and over 43 terabytes of data. Now, when we began to analyze these workloads, based on all the media coverage at the time, we were expecting it to be dominated by a very large number of video downloads, that is, audio clips. But in fact, it turns out that this workload is dominated by a very small number of very large video downloads. Now, one simple way to think about these workloads is to think in terms of ants, mice, and elephants. A web page is like a 5 to 50 kilobyte sized ant. An audio file is like a 5 to 10 megabyte sized mouse, whereas a video file is like a half to 1 gigabyte sized monstrous elephant. Now, I understand that you all know the size difference between an ant and an elephant, but let me just suggest a couple of back-of-the-envelope calculations. Just 2 video downloads, just 2 of them, would consume more bytes than a typical user's entire year's worth of web downloads. Now, I want you to think about something here. Today, we already have legal movie download services available at movielink.com and cinemanow.com. Suppose in the future, these movie services get more widely deployed, and suppose we begin to download at the rate of 1 movie per week rather than 2 a year. Just imagine what it's going to do for the web workloads as we know them today. Just imagine the kind of impact it would have on the internet workloads. In other words, the elephants are already crushing the ants and the mice as I speak today. But in the future, there is a possibility that we're going to see an order of magnitude more of these elephants. Yes?
I think I've heard it's commented previously that the existence of something like a proxy cache at the border of the University of Washington would greatly reduce the amount of traffic due to the peer-to-peer system.
Yes.
So presumably in this hypothetical future, one could make an optimization like that, and it might be that even, tell me whether I'm right or wrong, is it the case that you could have less traffic due to the peer-to-peer file sharing system, even if the number of video downloads went up?
It is possible. So essentially, you're suggesting an infrastructural design that does not exist today, which can reduce this traffic. And actually, that's one of the things that I'm going to talk a lot about in the later part of the talk.
All right. Doesn't that infrastructure already exist today for the web?
Yes. But even without that infrastructure, I still think, because of essentially this back-of-the-envelope calculations, that video, it's more to do with the sizes of these multimedia workloads than with the peer-to-peer infrastructure that exists today. That is, I actually believe that in the future, if we are ever going to see a future where these multimedia workloads are going to be transmitted over the internet, then it will be these multimedia workloads that will totally dominate over the web workloads.
It's going to depend upon the popularity. If you're assuming that the popularity index would be something like zips again, right? What if the most popular video file is dominant? What if that exponent, alpha,
Yes.
was completely different?
So
what if everybody wanted to watch the most popular movie for most part, and there were only some freaks who would want to watch a movie made in 1960 or something?
I think essentially here we're jumping ahead. In fact, a lot of this talk is about how we're going to exploit those locality to design such caching infrastructures, which is essentially the solutions that you're proposing, is what I'm going to discuss in the later part of the talk. Yes?
The sense I get, though, is that there's really a lot of elasticity of demand here, which is that the reason why people are now downloading these movies is because the bandwidth is there. That is, in other words, to say it seems potentially a little bit disingenuous to say, uh-oh, what if there's 10 times as many movie downloads? You could have said that 5 years ago, but I think the reason that there are movie downloads now is because it didn't work before.
So I was making this comparison of one movie a week,
Right.
is because that's the rate at which sometimes I watch movies, and I believe a lot of people watch movies at the rate of one movie per week. So I don't know why that would. Are you saying that you don't believe that people might want to watch one movie per week?
I'm saying I think people watch as many movies as the infrastructure will support in some sense. And
Yes.
to extend your analogy, there was an anthill and a lot of ants were going in and out of it. And then one day somebody built instead a doorway the size of an elephant. And so naturally elephants started moving through. And so if there's now, a 10 times as big of a doorway, then maybe 10 times more elephants will go through it. But it's not that there was an elephant trying to break into the anthill 10 years ago.
So essentially, if I get your
What happened to the mice?
so
Stomped on the little.
It was too complicated an analogy.
Yeah.
So I think today the multimedia workloads are dominating over the web workloads, but they're still not dominating to the extent that they could have if we had the necessary infrastructure. And I think as people who work in technology, I think it's our responsibility to actually design the infrastructures that could satisfy this demand, right? And the point that I'm making here is that there is this lot of demand which the current infrastructure cannot simply keep up with. Yes, Venkat.
So I don't quite agree. I mean, maybe you're implying that because in terms of total byte count, things like video download is going to sort of far outstrip anything else.
Yes.
The design of the internet should really primarily focus on that kind of workload. But I mean, if I think about me as a user, okay, let's say I download one movie a week,
Yes.
but I visit 100 websites in a week.
Sure.
Okay.
Definitely.
It's like I'm doing 101 activities, of which if 100 of them really do poorly, and then the one that's downloading the movie does very well, I may not be as satisfied as.
I'm not saying that we should focus the infrastructure design just to satisfy the video workloads. All that I'm saying is today we already have the infrastructure in place to handle the other type of workload. We don't have the infrastructure in place to handle this type of workloads. So what is it that we need to do to essentially make these downloads scalable and things like that? So yes, these workloads are essentially dominating in terms of the number of bytes. They're definitely dominating in terms of the number of requests. Yes.
One more thing you have to consider, I think it's something along the lines Venkat is saying, is that whether the video is being watched in a download completely and then watched, or are you watching it in a streaming fashion? I also watch one movie a week, and I order it on my pay-per-view cable system.
Yes.
And it is streamed, right?
Yes.
So those are two different things.
Yes.
And you would have to design the underlying infrastructure in completely different ways to support one versus the other.
Yes. In this talk, I'm going to consider only movies that are completely downloaded. Though many of the request distribution characteristics that I'm going to discuss might be applicable for streaming media too. So again, I think this is this confusion between workloads and the infrastructure. I want to keep both of them very separate. I'm going to examine multimedia workloads, but many of the characteristics that I'm going to talk about are applicable even to the streaming workloads. It's a different infrastructure, though. Okay? So naturally, the question that we asked was, what can the design of the web teach us about Kazaa? So we looked at the Kazaa request distributions. And interestingly, but perhaps unfortunately, we noticed that Kazaa video request distributions actually do not obey the Zipf's law. Now, this graph here, similar to the one that I've shown you before, x-axis shows objects ordered by their popularity, and y-axis shows the number of requests that go to this object. In green, I show the Kazaa video requests, and in blue, the best fit Zip distribution for these requests. Now, this graph shows that Kazaa video deviates significantly from the best fit Zip distribution. And unfortunately, this deviation happens towards the head of the distribution where you have a majority of the requests in the workload. Now, intriguingly, it turns out that it's not just Kazaa workloads that exhibit this behavior. Many other multimedia workload distributions, such as video rentals in the top graph here and movie box office collections in the bottom graph here, both of those also exhibit this non-Zip behavior. Now, we got this data from the publicly available Internet Movie Database site, imdb.com. Now, we wanted to understand what the implications are of these differences. Now, to understand that, first, we wanted to understand why these multimedia workloads exhibit this non-Zip behavior. What factors would be driving these non-Zip behavior? So we looked at our trace for some clues, and we found something really interesting. It turns out that most of the time, a Kazaa user downloads a Kazaa object at most once. Now, we thought about why that would be the case, and we realized something very fundamental. There is a fundamental difference in the notion of an object in the web and an object in the multimedia or in the Kazaa workloads. An object in the web refers to a point of interest, whereas an object in the multimedia workloads refers to specific content. So as a result, a web object can be updated or changed over time, whereas a Kazaa object cannot be changed. It's immutable. For example, users visit popular sites like NewYorkTimes.com and CNN.com repeatedly over time because they're updated over time. But in contrast, Kazaa objects are immutable. Whether you watch the movie Terminator today or 10 years from now, you're going to see the same movie, the same content. Now, because of this, there's very little incentive for a Kazaa user to download an object more than once. Now, sometimes in the web, we do tend to download web pages that do not change that often. For example, my homepage or a department web page. Now, we do that because these web objects are very small, and it takes trivial amount of time to download these pages. But in contrast, Kazaa objects are very large, and users would prefer to cache the object on the local disk rather than re-download them all over again. Now, because of this, a user in Kazaa tends to download an object at most once. Now, this simple and almost trivial observation has many interesting implications. Right off, the number of requests to an object, independent of the popularity of an object, is bounded by the number of users within the system. Now, this might be able to explain why we notice such a flat head in the request distributions. Now, it turns out that this fetch at most once behavior actually causes many other interesting object and user popularity dynamics. For example, in Kazaa, an object popularity is very short-lived, and most of the popular objects tend to be very young. Now, to understand this, let me once again take the analogy of movies. When a new movie is released, it's at the height of its popularity. All of us want to watch the movie on the very first weekend of its release. Now, unless you have kids, you're not likely to watch the same movie again. Because of this, on the subsequent weekends, the popularity of the movie falls off very steeply, and it's eventually replaced by a new movie. We see that happening here. Kazaa workloads are driven by new objects, object births, rather than by object changes. Now, our trace also shows that new users are an important driving force for this workload. This is because when a new user joins the system, her entire movie or music collection is empty, and she can download any movie she wants, be it the latest releases or old classics, Citizen Kane, Godfather, whatever. But over time, this user is going to exhaust all the old popular objects, and she will have to slow down her rate of requests to the rate at which new movies are being added into the system. So we see these effects going on in our trace. So overall, the factors that drive these multimedia workloads are very different from those that drive the web. The web is primarily driven by fetch many behavior and object updates, whereas Kazaa is driven by fetch at most once and new objects and new users. Now, to understand these workloads, we need a new model or a new framework to think about them and to reason about them. Now, such a model would also be useful because it would help to formalize these intuitive ideas that I've been talking about so that we can validate them with a trace. So that's exactly what I'm going to do next by proposing a new multimedia workload model. Now, this model is based on a very simple, intuitive, but very powerful hypothesis. I'm going to assume, and I'm going to validate this assumption later, that I can explain why these multimedia workloads exhibit non-ZIF behavior starting with a ZIF distribution and by adding to it the fetch at most once behavior and new objects and new users. So this model has 4 simple components. First, I assume that users do in fact request these objects from an underlying ZIF distribution. Now to this, I'm going to add the fetch at most once behavior. To attach this restriction, I maintain individual copies of the distribution, 1 per user, and whenever a user picks an object, I remove it from a distribution. Now when I add new objects, I insert them with an initial popularity that is picked from a ZIF distribution. When an object is inserted at a position, I push down all the objects that are less popular than it by 1 position down the ZIF curve. And by picking the initial popularity of an object from a ZIF distribution, I can make sure that I preferentially add new objects towards the head of the distribution. Now this way, I can guarantee that we see significant turnover among the popular objects, that object popularity remains short-lived, and that most of the popular objects remain young. Yes, Venkat?
I don't understand number 4. So you have a separate curve for each user?
Number 2.
Number 4. New users begin with a fresh zip curve or whatever.
Yes. So when we add a new user, we make a fresh copy of the ZIF distribution and give it to them. So there is a base underlying ZIF distribution, and we maintain individual copies per user. We need to do that because to enforce fetch at most once, when I pick an object, only my curve changes, but nothing else changes. But when we add new objects, everybody's curve changes. So there is a base ZIF distribution that is being replicated per user. Each user picks from their own distributions. But new objects are added to the base ZIF distribution whose effect is then replicated across all the distribution. Yes, Jit?
Wait, I don't understand this now. So if I fetch a particular object, the popularity as I perceive of other objects in the system would change for me?
No. The relative popularity of the other objects in the system would remain the same.
What he means is then you'll pick some other object next. So effectively, that's changed the distribution that you pick objects with.
Yes.
So the ZIF distribution that's maintained per user would change because of 2 reasons. One is the new object is added, it's going to change the distribution for everyone.
Yes.
And on top of that, you modulate it based on what you guys already downloaded.
Yes. Yeah. Because the fetch at most once is pretty important for us to take care of.
You reset.
Yes.
You need a user model then here also, right? To model the arrival of new users and maybe virtual users.
Give you a new distribution. Object number.
Yes. So this is actually, we had a much more complex model that we analyzed, and we realized that, I'm going to explain a little while later why users have actually new users have limited effect on the request distributions. So yes, this is a very base, simple model. On top of this, you can build more complex models. And we are not capturing every single detail, but our goal is to capture just this basic properties of the model so that we can explain the request distribution.
Oh, so I'm not making any claim about the representativeness of this model. It just doesn't, I'm trying to understand the definition of it, which is that you're saying new users, but what defines when a new user comes in? In other words, what is a new user according to this model?
So we have, maybe it will get answered. So we add new users to the system, and when a new user is added to the system, then we make a fresh copy of the ZIF distribution and give it to them.
Right.
The question is when do you add new objects?
When do you
The same thing for new objects. How often new objects arrive?
Oh, so those are the parameters that we can vary. So actually, our model has several different parameters, and these parameters actually correspond to the components of the model. So we have number of clients, number of objects, object arrival rate, and client arrival rate.
And then those are like Poisson arrivals or something?
You can play with it. Now, the output from this model is a synthetic trace of workload requests that maps objects to users over time. And the good thing about this model is that you can plug in various different values to these parameters and essentially generate various different synthetic traces. And by comparing the synthetic traces, you can understand how the request distributions would vary with changes to the components of the model. So that is, in fact, the goal of having this model, so that we can isolate the effects of various different parameters and then play with them, which is what I'm going to do next. Okay? So we wanted to, at a very high level, check whether this model would be sufficient to explain this non-ZIF distribution that we are seeing for these multimedia workloads. So we parameterized this model with values that are drawn from the trace, and we compared its output, which is a synthetic output, with the actual measured trace. So the results I show in this graph here. There are 3 request distributions. The green curve shows the measured distribution that we saw in the trace. The blue curve shows the ZIF distribution that explains the web workloads very well. And the red curve shows the distribution that is predicted by our model. Now, clearly, the green and the red curves match pretty closely, which validates our model. Now, I want to emphasize something here. The goal of the model is not to imitate the trace 100%. Instead, a good model, I believe, should be simple, and yet it should intuitively capture the fundamental properties of the workloads. Now, the interesting point in this graph is that we are able to describe 43 terabytes worth of data points using a simple model that has 4 intuitive components. Yes, Mike?
You said that your model matches reality well, but I mean, on what basis do you say that? Because if you look at the y-axis, that's a log scale, and I see sort of a gap there, I mean, on the left hand, which could be quite significant. So, did you do? I mean,
so we have we use the mean squared error fits to check how well this matches. Is that what you're referring to?
Yeah, because looking at it, I wouldn't say that the left hand really matches that well, because it's a log scale, and I don't know what those 2 numbers are, but there is.
You mean that part?
Yeah.
Yeah, it could be, what you're saying, 300 and 400, for example, or
Whatever, yeah. I mean, it's.
Yes. So this is.
Your model is flatter than the other guy, right? In some sense.
Yes. So we do see for certain number of first few objects the curve deviating a little bit. So we're never going to be able to match 100%. So we're always going to see some error. So this is a curve that sees the least error according to some error function that we used. Now, I don't think we're ever going to be able to match it 100%. I don't think even in the web workloads we do that.
Sure. I was just wondering if you had any insight into why that was happening.
Oh, that was because some of these users tend to download an object more than once. Most of the time, they don't. Like 95% of the time, a user downloads an object more than exactly once. But then there is this 4 to 5% of the time when they download twice or thrice. Essentially, that thing adds up there, over there. Yes?
I must have missed something a while back. Can you explain object popularity again? What is meant by that?
Oh, by object popularity, I mean it's technically the object rank. Essentially, we order the objects based on their popularity, based on the number of requests that they received. So the 0.100 refers to the...
How could you graph them against the number of requests if it's just a direct relationship?
To make it monotonic.
Okay. So this point here refers to how many requests on the y-axis did the 100th most popular object receive.
like sort of the objects by file name, but it'd be bumping all over the place. You wouldn't see anything, right? It'd be a mess of points.
A 100th object is not the one that received 100 requests. 100th object is the one that would have received 5 requests, for example.
Okay.
Yes.
Okay.
Yeah.
Okay. So far, we looked at how the multimedia workloads differ from the web workloads. We have proposed a model, and we validated the model. So what are we going to do with this model? So one of the toughest challenges in delivering these multimedia workloads, as I mentioned before, lies in the amount of bandwidth they consume. In fact, in 2002, University of Washington estimated that its peer-to-peer bandwidth was costing it more than $1 million per annum. So naturally, we were interested in seeing what kind of bandwidth savings we could get if we were to exploit the locality in these requests. Or in other words, how cacheable are these workloads? Now, we analyzed our trace, and we simulated a hypothetical university-wide proxy cache. And we found that a surprisingly high 85% of the bytes could have been saved by this cache. Now, when we looked at this number again, we had 3 questions in our mind. First, it surprises because in the traditional web workloads, we are typically used to seeing cache hit rates between 40 to 50%, nowhere close to the 85% number that we are seeing here. Yes, Ellen?
Are you looking just at downloads, or are you also looking at University of Washington Kazaa users who are serving external people?
No, we are just looking at the downloads. Only downloads. It's that.
May be coming to this later, but you mentioned earlier the issue of how the distribution model or business model, or whatever, may change over time, and that could affect this radically, right? If, for example, content were encrypted differently for different users.
Yes, sure. It's possible that if each user were to be given their own encrypted content, then it might change. Yes. I can talk more about that later in terms of how iTunes works today, because they face a very similar problem.
So in coming up with this percentage at 85% of bytes, did you also consider, what if some of the UW clients are sharing the file amongst themselves in a secure fashion?
We ignored the local file traffic. Now, there are reasons why we believe that the local file traffic is, essentially local traffic between the university peers is not a considerable fraction of the overall traffic. And I can go into the details later. We did some sanity checks for that. Okay? So, again, getting back to the point. When we looked at this thing, there are three reasons why we were a little bit suspicious about this number. First, in the web workloads, traditionally you see between 40 to 50% hit rates, nowhere close to 85% hit rate. Second, at the very first glance, it kind of seems funny that a workload where the number of requests that go to the popular object is restricted by the fetch at most once should actually see such very high hit rate. And third, we were very concerned that what we are observing might be some measurement artifact that is peculiar to university population. So the advantage now is that we have this model, so we decided to understand what's going on here by using this model to study how the cacheability is affected by fetch at most once and new objects and new uses, so that we can identify which is the dominating factor and which is a factor that is likely to be replicated in practice in the outside world. Okay? So let me begin by looking at how fetch at most once affects the cacheability of the Ceph distribution. Now, in this particular analysis, I'm not adding any new objects or new users. In this case, it turns out that exactly as our intuition would predict, fetch at most once destroys the cacheability of the Ceph distribution. This is because without new objects or new users, existing users would exhaust all the objects at the top of the Ceph distribution, and then they begin to slide down the Ceph curve into this ocean of unpopular objects. And as they do this, the cacheability of the workload constantly degrades over time. And that's what we see here. X-axis shows the time, y-axis shows the hit rate. Fetch many Ceph distribution maintains a constant hit rate, whereas fetch at most once restriction, the hit rate constantly degrades over time. Next, we began to add new objects to the system. Now, when you add new objects, they replenish the old popular objects. And because of that, they have the effect of pulling the users who are sliding down the Ceph curve because of fetch at most once back to the top of the Ceph curve, where you have the popular objects that are very cacheable. Now, our analysis shows that adding new objects at a constant rate, independent of however small the constant rate is, it always leads to stable long-term hit rates. So x-axis here shows the number of new objects per week, and y-axis shows the long-term stable hit rates. Now, the hit rates increase with the object arrival rate. Now, the most interesting part of this graph lies in these points here in the top right corner. These points show that we can achieve very high hit rate, as high as 80%, with moderately small object arrival rate of about 7 to 8 new objects per week. Now, in the real world, Hollywood, in fact, releases new movies at the rate of 5 to 10 per week. Now, I really want to emphasize the importance of our analysis here. When we saw the 85% number for the first time in our trace, we were suspicious that it might be some measurement artifact that is peculiar to university population. Now, this analysis, on the other hand, explains to us why we should, in fact, be expecting to see such kind of hit rates in practice. It increases our confidence that the reason why these hit rates occur in practice is because of the rate at which new movies are being released into the system. Yes?
Are your traces just for movies though, and not music?
So we focused on primarily video, movies.
And how did you determine that? Just the size?
We have, when these objects are downloaded, they have a HTTP header part of it that indicates what's the type of content, audio, video, and so on. Now, there are reasons why I'm not talking about music here. The simple reason being they're not a significant fraction of all the bytes. And there are also other reasons about how well this analysis applies to music, and I can talk about that later. Okay? So next, we stopped adding new objects, and we began to add new users. Now, new users tend to increase the hit rate because they start with a fresh zip distribution, and they have all the popular objects to download from. But over time, new users begin to grow old. And as they do this, to maintain a stable hit rate, we need to add new users at an exponentially increasing rate, which is not possible in practice. It's infeasible. So the takeaway point here is that new users have limited effect on the cacheability of these workloads. So overall, our analysis explains to us why caching works very effectively for multimedia workloads, and this is primarily because of new objects. And so this forces us to rethink certain aspects of our delivery infrastructure to quickly redistribute these new objects. Now, this is a little bit trickier than what you might think. This is because traditionally, replication strategies have relied on the past popularity of an object. Now, past popularity matters very little for these workloads. What matters is the instantaneous popularity. For example, the most widely replicated object in the Kazaa system today might be Spider-Man 2, which was released a year ago and is therefore no longer the most popular object in demand today. Now, in this respect, some of the more recent protocols, such as BitTorrent, might be more useful because their architecture tends to leverage or thrive on the instantaneous popularity of an object. Yes, Victor?
So I was thinking, you tend to focus on movies, and you sort of led us to believe that you've got so many movies being released, etc. But movies are not the only video content, right? Like, there's going to be a lot of news, lots of other things. So there'll be lots and lots of objects that are video that are not movies, right? Yes. And then to sort of say, okay, we're going to cache all of those. I mean, I'm not sure I understand how many of those and which ones you go and get them, given the fact that there are so many of these objects around, which are video and which are very heavy.
So there are many other different types of workloads. In fact, you're raising a very important question, which is what happens when you begin to talk about TV serials or something like that. In some sense, when you begin to talk of TV serials, you will begin to go back to the web kind of model, because you have the 7 o'clock show or a Seinfeld show or a Simpsons show this week, which is, again, a point of interest rather than the specific object itself. Now, in fact, there are other researchers, some people at Rice and other researchers like that, who are actually adding these components on top of our model to examine what would happen. So we didn't examine those kinds of workloads, but it's imaginable that somebody would modify this model to accommodate various different systems. But yes, it would change. The model should change.
Are your inferences of your workload unduly influenced by the Kazaa system itself, in that if I wanted to download an unpopular movie, yes, and I did the search, and there are very few Kazaa users who have that I can grab it from, and so I'm unsuccessful in getting it because those 1 or 2 users is down. Is your analysis then going to be kind of skewed more towards the popular ones because of that?
Possible. I cannot say with absolute certainty, or in fact, I cannot rigorously argue that it isn't. That's the reason, actually, why we were essentially drawing these comparisons between what we are seeing on Kazaa and what actually goes on in the real world. That is, we are comparing with the data that we are obtaining from imdb.com and so on. We are comparing the rate of new objects that we see in our system with those that is going on in the real world. But at the end of the day, I cannot rigorously argue that this is absolutely right. But I hope that it isn't. And that's the reason why we're using these other data sources as checks.
So then when counting object popularity, are you looking at the requests or successful downloads, or searches for that object, or what is the...
We are looking at downloads. We are not looking at searches, because oftentimes a user searches...
And when you say download, do you mean successful download or request for download?
We were looking at successful downloads.
Okay.
Because sometimes if the download is not successful, then the person is going to re-download the object again. Yes.
So you analyze this with 8,000 object cache size?
Yes, we analyze this with various different object cache size. Yeah, the one that I showed you with is 8,000 objects. which will mean about 8 terabytes of cache, which sounds a lot, but I think in the future it's not going to be that difficult to have that kind of caches. We built storage systems like a terabyte storage system with 2,000 bucks or something like that using traditional.
In the design of the system, users become caches, essentially. I'm not sure I understand the interaction. I mean, there's a big difference between the web there, which is that if I download a popular object, I can't then serve it to anybody else.
Yes.
Whereas with these file sharing protocols, that's in fact exactly what they're supposed to do. So it seems like as the popularity goes up, the probability that you don't have to go through the border router should also go up.
Sure.
There should be somebody on your side of it who has it.
Yes, that's a very good question. So in this talk, I just focused on the workload part of this research. Now, we looked at locality-aware caching architectures. In other words, rather than having a hypothetical university-wide proxy cache, suppose if we could redirect this request somehow to peers within the university, what kind of hit rates would we see? Because that actually has some interesting things going on in there because of the availability of peers and things like that. Now, I'm not going to cover that in this part of the talk, but I'll be happy to talk about that later.
One more question.
Okay.
You're talking about 85%, you can cache 85% of the requests.
Yes.
And then comparing that to the earlier graph you show about the World Wide Web is here and peer-to-peer is here, it sounds like because the legal landscape changed, we were able to deploy the exact same proxy cache for the multimedia workload, it would disappear almost from the graph. It would now become less than the web workload.
Sure, possible.
Okay.
And yeah, so it's actually a great incentive to do that, right? I mean, currently we don't have that infrastructure, and essentially I'm arguing that this infrastructure actually makes a lot of sense.
Okay.
So the fact that without this infrastructure, this workload would be dominating is a motivating factor to deploy this infrastructure.
Okay.
Anyways, so to summarize, multimedia workloads have broken out as a major source of bytes in the internet today. These multimedia workloads are very different from the traditional web workloads. Many of these key differences originate out of few intuitive fundamental factors that drive these workloads. We have huge multimedia objects that are immutable, and as a result, they're fetched at most once. And this fetch at most once indirectly leads to very interesting dynamics of object and user popularity distributions. Now today, I proposed a new model explaining these key factors in the workload, and I discussed some of its implications. So with that, I'm going to move on to the second part of the talk.
Just one quick question. Did you make
We will not finish this.
Okay, fine. Well, I'll ask later.
We will not finish
Yes.
Fine. It's not important.
So I'm going to shift some gears here. In fact, I'm going to shift several gears. I'm going to move from internet workloads to internet routing. And the question that I'm going to address here is how we can improve internet path reliability using a special form of routing that we call source routing. Now, source routing is a very simple idea. You have a network and a bunch of hosts that are connected to this network. You have a source node and a destination node, and a path that goes over this network, which is shown in pink. Now, when this path fails at a certain point, contrary to what you might expect, today, paths in the internet take quite some time before they recover. So the source node, during this time, rather than just sit and wait for the default path to recover, can ask some intermediate node located elsewhere within the network to help route the packets to the destination. So if I cannot reach Victor directly, I can request Alec to help forward my packets to Victor. Because I, the source node, am making the routing decision, we call it source routing. Okay? So what's the problem here? There has been lots of research into these source routing architectures in the past. However, most of the schemes never rely or exploit in-depth knowledge about internet path routing or path failures. As a result, most of the existing architectures maintain complex routing state and do complex path monitoring, and as a result, they tend to be unscalable. For example, the state-of-the-art system maintains state about all paths between every pair of nodes in a system. As a result, if you have n nodes within the system, the amount of state that you maintain grows as order n squared, and very quickly, the system becomes unscalable. So our goal today is to understand internet path failures in sufficient detail to be able to design simple yet scalable source routing systems. Now, I'm going to achieve this by answering 3 questions. First, what are the failure characteristics of internet paths? Second, how can we leverage these characteristics to design simple yet scalable schemes? And third, what benefits would end users see in practice if these schemes were to be deployed for a real application, such as web browsing?
You just spent first half of the talk telling us that most of the traffic is not web browsing, right?
Yes.
So why would you not focus on that instead?
Oh, because So with respect to the reliability part of it, in peer-to-peer, there is already the source routing going on at some level, at an application level. In peer-to-peer, in fact, a lot of source routing is going on, so it doesn't really make sense to talk about source routing in that context, right? Okay, so to answer these questions, once again, we conducted a measurement study, and this time, this is a different measurement study that relies on a week-long week-long duration of probing a large number of internet paths. So I probed over 3,000 destinations from 70 different Planet Lab sites. Now, Planet Lab is this measurement testbed that has hosts in universities and research labs across the world. So we had hosts in both North and South Americas, Asia, Australia, Europe, and so on. Now, we probed each path at a peak probing rate of 1 probe every 5 seconds. And whenever we see probe failures, we use traceroute to find the location of failure, where the path failure happened. Now, we declare a path as having failed when we lose 3 consecutive probes over a period of 15 seconds, and as well as a traceroute failure. Now, when selecting, yes?
But where did you get the 1,000 broadband hosts from?
Okay, so we selected these destinations from popular servers, about 500 and 1,000 broadband hosts. So these broadband hosts are selected from all the major cable and DSL providers in the US, Comcast, AOL, Time Warner, Quest, Verizon, SBC, Bell South, so on, as well as some across the world, like in Europe and Australia. The reason why we were able to select these is because we already had these traces from this peer-to-peer measurements before, which gave us the IP addresses of where the various different hosts are located. So we probed the IP address space to detect more IP addresses.
Well, how could you know that that IP address was, if most broadband hosts have DHCP-assigned IP addresses?
Yes, right? So when we do a reverse lookup on the IP address, the name very clearly indicates what kind of a host it is. For example, a host in SBC will say something like la.sbc.com, ADSL _ la.sbc.com. So we use those pattern matching.
Will it also tell you that the host was out? No.
No. So that's a limited. You're jumping ahead a lot, in fact. So that's a limitation of a methodology which I'm going to handle by classifying those destination failures. So at a very high level, we wanted to understand 3 characteristics of path failures. How often do paths fail? How long do these failures last? And where do these failures occur? Now, understanding these characteristics is important because these affect the effectiveness of recovery using source routing. Now, I'm going to very quickly summarize these results here. How often do paths fail? Well, failures do happen. We see them almost on a daily basis. The takeaway point here is that failures happen often enough that there is a case to be made for the deployment of source routing to fix these failures. How long do failures last? Failure durations tend to vary a lot. Most of the failures tend to last several tens of seconds, but still, they're less than 2 minutes in duration. So if you were to look at the median path availability, it's pretty high. It's about 99.9% for all the paths. However, there's some fraction of failures, about 10% of them, that last very long, more than 30 minutes. So if you were to look at the mean path availability, it's only 99.6% for servers and 94.4% for broadband. That's usually referred to in the industry as the 2.9 availability and 1.9 availability for broadband. So the takeaway point here is that most of the failures are short enough that any recovery scheme used should be inexpensive under the normal conditions. Because most of the time, the default path works just fine, and you need to invoke this recovery scheme only when the path fails for a short duration once in a while. Finally, we wanted to understand whether failures occur within the middle of the network or towards the edges. So if you take an internet path today, it goes through 4 or 5 different ISPs or networks. You have the local ISP on the source and the destination side, and in the middle, you have the big Tier 1 ISPs. Tier 1 ISPs are ISPs like AT&T and Sprint. Now, based on where the failures occur, we classify them into 4 categories. If the failure occurs within a Tier 1 ISP, we call it a core failure. If a failure occurs near the source or the destination side, we call it the source side or the destination side failure. Now, on the destination side, we cannot distinguish between failures that happen on the last link and the failure that happens because of the destination node itself failing. Now, the reason for this is that we don't control the destination node. We control the source node, which is a measurement machine within our Planet Lab network, measurement testbed. But the destination node is a server or a broadband host that we have no control over. So we categorize those failures into last hop failures. Now, server path failures tend to happen throughout the network, whereas most of the broadband path failures happen on the last hop. Almost 60% of them happen on the last hop. It's an interesting number to know, but it's not particularly surprising because broadband hosts tend to be less well maintained, as well as their links tend to fail more often. The takeaway point here, though, is that because source routing works by leveraging the presence of alternate paths, server path failures are more likely to be recoverable than the broadband path failures. Next, we wanted to understand what fraction of these failures are recoverable using source routing. So we evaluated a special form of source routing that we call one-hop source routing. Now, in one-hop source routing, an alternate path is permitted to have at most one intermediate node. In other words, if I'm not able to reach Venkat, I'm allowed to ask Alec and Victor separately to help me route to Venkat, but I cannot ask Alec to route first to Victor and Victor then to route to Venkat. Okay? Now, it's an interesting question to ask whether having more intermediate nodes in an alternate path can actually help in recovering from more failures. Now, we did a separate graph theoretic analysis of the internet routing graph that convinces us that having more intermediate nodes in an alternate path does not necessarily help in failure. But I'm not going to talk about that here. I'm simply going to assume that one-hop source routing is as effective as generic source routing. So to evaluate one-hop source routing, during each one of the path failures, we sent probes using intermediate nodes located at 40 different Planet Lab sites. And we compared the success of probes along the default path as well as the intermediate paths to estimate two things. One, the maximum potential of any source routing scheme, and the success rates of specific but different source routing schemes. So to evaluate the maximum potential of any source routing scheme, we declare a failure as being recoverable even if one of the 40 intermediate nodes that we probed helps in routing around the failure. Now, this table here shows the recovery percentages for both server paths and broadband paths. The first line here shows that we can recover from almost 66% of server path failures, but only 39% of broadband path failures. Now, this difference is primarily because of the last hop failures. Interestingly, for failures within the core of the network, remember, core failures are the ones that happen within the tier 1 ISP, so they tend to affect a larger number of paths simultaneously. We can recover from almost all of them, about 90% or so. So overall, these numbers suggest that source routing might be a viable strategy for recovering from failures. However, we still have a problem. We obtain these numbers by probing all the intermediate nodes. So our next goal is to try to achieve the same recovery percentages, but by using or selecting far fewer number of intermediate nodes intelligently. Okay? Now, to answer that question, we looked at what fraction of the intermediate nodes actually help in recovery. The basic idea here is very simple. If exactly one node helps me in recovering from a failure, then I need to be very careful about how I pick the one node. But if a large fraction of the nodes are useful in recovery, then I can pick pretty much any one of them. So the good news here is that it turns out that for most of the recoverable failures, half or more of the intermediate nodes are useful in recovering from it. So all that we need to do is to avoid a few bad apples. So this immediately suggests that a random choice of intermediate node has a pretty good probability of succeeding in recovering from the failure. So next, we evaluated a random K policy. Now, in random K, a source node picks K intermediate nodes at random and tries to route around the failure simultaneously by probing all K intermediate paths. Okay? And if at least one of the paths is useful in routing around the failure, we call it a success. So in this graph here, x-axis shows K, which is the number of attempted intermediaries, and y-axis shows the fraction of failures that we recovered using these K. The top graph shows for server paths, and the bottom graph shows for broadband paths. Notice how both these curves show very similar characteristic traits. They rise pretty steeply for very small values of K, but by the time they reach about K equals 4 or 5, the curves begin to flatten off for the rest of the graph. So what this shows is that beyond a small number of intermediate nodes, selecting more and more intermediate nodes does not necessarily help in your recovery. In other words, random 4 delivers near optimal performance. And no matter how smart a policy you use and how hard you try, you simply cannot do much better than that. Now, the good news with random is that it requires no a priori probing state, it requires no path maintenance, path state maintenance, and therefore it involves no cost whatsoever in the common case. Now, finally, we wanted to validate this random 4 policy for a real application, which is web browsing. So we implemented a real system that we called Saucer, which is scalable one-hop source routing. Now, there are a couple of interesting points about its architecture, but in the interest of time, I'm just going to skip over that. And I'm just going to go to evaluation of the Saucer implementation. We ran 2 clients, one with and another without Saucer. Now, both these clients ran from UW, and they repeatedly fetched web pages from 1,000 popular servers over a period of 3 days. We deployed intermediate nodes at 40 different Planet Lab sites. Now, here are some very high-level results. During this time, we issued over 250,000 web requests, and the default client succeeded 99.8% of the time, which is what you would expect from our previous measurements. Now, the good news is that a Saucer user sees 56% fewer network path failures, which validates the random for policy because it's close to the 60% number that we have seen before. Now comes the bad news. Now, when a user is browsing the web, there are many different types of failures a user might see. And network path failures are just one category of failures. There are other failures, such as a web server might refuse a HTTP or a TCP connection because the server is busy or the server has crashed. Now, end-to-end reliability of any application depends both on the reliability of network paths as well as application software. Now, Saucer, being a network-level mechanism, cannot recover from application-level failures, so any application-level failures tends to limit the overall utility of Saucer. Now, unfortunately for us, it turns out that for the web, we see a large number of application-level failures, almost twice as many as we see network path failures. So I want to be very clear about the implications of this negative result. I'm not claiming that Saucer is not useful in general. All that I'm claiming is that for the web application, for the web, as we have it today, Saucer has very limited utility because even if you were to fix all the network path failures, the end-to-end reliability of the web application would still remain 3.9 as we have it today. Now, this is because of the direct application of the Amdahl's law. However, it's conceivable that in the future, when more reliability demanding applications would come up, such as voice over IP, then this might be more, Saucer might be more useful. Remember, in voice over IP, the end instrument is a dumb telephone box which can simply never fail. Yes?
The question I was wondering is, do Saucer users tend to see more app-level failures than the default user? It's because there is one extra hop involved, the chances of a TCP timeout perhaps go up or something like that.
Yes. We do see that happening a little bit, yes. But it's not to the extent that it offsets the advantages. So to summarize, source routing architectures have been proposed in the past to increase the availability of internet scale applications. So today, I presented a study of network path failures and their recoverability. Now, the good news is that we were able to design a simple yet scalable scheme that achieves the maximum possible benefit from source routing. The bad news, however, is that despite substantial efforts in the past, source routing has very limited utility for the web application that we have today. However, it's possible that Saucer might be more useful in the future for applications such as voice over IP. So to conclude, let me revisit the basic premise with which I started out this talk. I claimed that to design the internet scale systems of the future, we need to understand the internet of today. Now, to understand the internet of today, we need to measure it at scale, model its behavior, and experiment with it by deploying new systems. And today, I discussed the utility of this, what I call as a measurement-driven approach, in 2 very different contexts. First, in internet workloads, and next, in internet routing. Now, in the interest of time, I'm going to skip over the future directions, and I'll go directly to the questions.
We want to see your future directions.
So I'm going to talk very briefly about some possible future directions in this line of research. There are other things that I'm interested in, and I'm going to flash the side of the other work later. Now, the internet is a very vast system, and there are several aspects of the current internet that we still do not understand. For example, we don't understand many things about the broadband networks or where the performance bottlenecks are located. We understand very little about the structural vulnerability of the internet to distributed denial of service attacks. Now, I believe that understanding these aspects is very important to answer many of the open questions about internet scale system designs. For example, today, it's still an open question whether or not a peer-to-peer content distribution architecture is fundamentally more scalable and efficient than a centralized or managed distributed infrastructures such as Akamai for delivering very large files such as multimedia or operating system upgrades. Right? Like, for example, when Windows XP Service Pack 2 was released last year, it's my understanding that it took Microsoft several weeks to deliver the update to all the users, which is almost the entire internet. Now, it's an interesting question to ask whether one could use more peer-to-peer infrastructure such as BitTorrent to do this job. Now, to understand or to be able to answer this kind of question, we need to understand more about the broadband networks, the characteristics, where they're connected to the rest of the internet, and so on. And we need to understand where the performance bottlenecks are located and so on. Now, this requires us to conduct very large-scale measurement studies that haven't yet been done so far. In fact, the grand challenge for this line of research is this question: how do we conduct representative internet measurements? By this, I mean all the internet measurement studies done so far, including the ones that I described to you before, are based on measuring a small portion of the entire internet population. Now, how do we know that the sample that we're measuring is actually representative of the internet? Can we even conduct measurement studies that are representative of the internet? Is conducting such studies really useful in practice? For what properties of the internet can we conduct such kind of measurement studies? For what can't we do that? Now, there are some interesting ideas that I explored in this area, and I'll be happy to talk to you later on about them. But at a very high level, I do believe that currently with Planet Lab kind of an infrastructure, we already have sufficient number of distributed vantage points that we can actually answer this question about representative internet measurements for certain properties more concretely. I'll be happy to talk about that later. So I'll be happy to take any questions. And just so that you might want to chat with me later on, this is some of the other work that I've done. Yes?
On some of those tasks that you measured failures on, what was the mean probe loss rate when just over the course of the lifetime that you were measuring the task?
Oh, it's about somewhere around 0.5 to 1%.
So extrapolating that out, just assuming exponential distribution of kind of probe failures, what would that, how many kind of spurious failures would you expect to see?
So typically when we notice this 1% of failures, they tend to be very, very clustered. Okay. In fact, it is rare. In fact, I was personally surprised how rare it is to see one probe failure. In fact, I think what you're referring to is, throughout this talk, I treated failures as discrete events. Essentially, I said, I'm going to declare a path as having failed when 3 probe fails. Right? Now, it's an interesting question to ask, why did I take 3? Why not 4? And so on. So we actually did 2 types of analysis for all the graphs that I presented. One is using packet loss probabilities, and the other is treating failures as being discrete events. Now, rigorously speaking, I should have been talking only in terms of packet loss probabilities, because I don't know when a failure happened, because I don't have access to the network as such. I'm just basing it on end-to-end probe failures. So yes, we do have graphs, and just for the simplicity of explanation, I talked about failures as being discrete events. But yes, we did make sure that that probability doesn't roll off into being spurious failures.
Thanks.
How do you determine the location of failures?
So we use traceroute to determine the location of failures, and that definitely has some errors, right? I mean,
yeah, a lot of problems, like the reverse path.
Yes.
What did you do about failures that affected the reverse path?
So we essentially based it on whatever the forward path indicates as being the failure. So that does lead to certain measurement errors, and we.
Okay, in general, in your traceroute data set, what fraction of routers did not respond to traceroute requests?
Oh, we made sure that the paths that we were probing, the destinations we picked, were such that the paths were trace routable from the source to the destination all the way. So when we selected the destinations and which paths to probe, we made sure of that.
You managed to pick 3,000 such hosts where all trace routes were, and that didn't introduce any bias, so it was not like they all ended up in the same ISP or something where the ISP...
No. We had all those plots. In fact, so we actually spent almost 2 months just working on which destinations to pick. So I can show you a ton of data about that. I mean, we tried various different strategies. In fact, first we tried to pick destinations so that the paths from the Planet Lab nodes to these destinations would cover as many inter-AS links as possible and all sorts of strategies. We tried a lot of that. I had a lot of fun with that, but I can give you more details. Yes, we actually measured a lot more than what I was showing here.
There's one other question. Sorry.
Yes.
You mentioned this value of k equal to 4 that if you picked randomly among 4 peers,
yes,
4 intermediate hops.
Yes.
There is this piece of work from CMU which you might be aware of about multi-homing, and that says that four-way multi-homing get most of the benefit of whatever end-to-end performance and reliability and so on. Do you see any sort of connection between these results?
Oh yes, a lot. In fact, let me translate the question. I mean, I think the question essentially boils down to, let's ask a higher level question. Why are we able to pick these alternate paths? At some level, we are able to pick these alternate paths because some ISP is multi-homed at some level. Now, typically the term multi-homing is used for end host, but because of some ISP being multi-homed at some level, right? So an interesting question to ask is, what is it about the structural inter-AS connectivity of the network that leads to this property of 4? Now, that is a graph theoretic analysis that we did. And the basic intuition there is actually at a very high level, very simple. You have all the tier 1 ASs that are all interconnected with each other, right? So suppose you have a source connected somewhere, and then you have a destination ISP here. Now, if a failure happens within the core of the network, clearly if you pick any intermediate node located anywhere, there's a pretty good chance that you're going to avoid the failure within the core. That's very easy to understand. Now, suppose if your local ISP is singly home to a tier 1 ISP, then if a failure happens anywhere here, you can't do anything. You cannot recover from it. But suppose if a local ISP is multi-home, this is in fact what we observed in the trace. And say, typically when a local ISP is multi-home, they tend to distribute the traffic between the two ISPs. Say, suppose 50% goes there and 50% goes here. Now, this is an ideal number, but you can have some sort of distribution, even 10% there and 90% there and so on. That means almost 50% of the hosts, if this link fails, all that you need to do is to make sure that the intermediate node that you pick lies in that 50% of the nodes which try to reach this destination using this other multi-home link, right? And that's usually the reason why randomly picking a small number of intermediate nodes succeed. Now, this is a very highly simplified diagram of what I'm talking about. Essentially, overlay, the reason why we are able to recover from these failures is because ISPs are multi-homed at some level. Now, a very interesting converse problem to ask is, can we actually influence this multi-homing so that we can actually increase the performance benefits of overlay routing? Right? So currently I'm saying we can recover from 56% of the failure or 60% of the failure. Now, the reason why we're able to do that is because of the presence of alternate paths. Now, an interesting question to ask is, can we multi-home such that we increase those alternate paths much more so that you could benefit from these kind of schemes? Now, I think that is sort of the question that the CMU people were trying to ask, and put it in a reverse context, which is, how many ISPs do I need to multi-home to so that I can get the best performance? That's the way I tend to view it. They're like very interrelated questions. We're coming from one direction, they're coming from the other direction.